they go to the same location, and they go to the value of the function. Let me do a couple of things here. Okay, this is a general picture of a piecewise function. So we're starting to get into now a different class of functions. Piecewise, what do you think I mean by piecewise? Well, it's a function defined by pieces. Play on words. I want you guys to understand one important thing. You see this picture? Your function, this is a picture of some function, an arbitrary function. Okay? You are going around, let's see what that value is. 1, 2, 3, 4. Okay. Let's see if you can read this. If I said, what's the limit as x goes to 4 from the left of the function f? We don't know what it is. We just have a picture of it. I'm asking for the left-handed limit. Is that true? So I'm approaching, you say, are you approaching Mr. Judge 4 from the left? I'll say yes. But remember, we're really talking about the y coordinate now, right? So every point on that curve going to this location from the left, could you guys tell me where I'm going? Where's the y coordinate? Is it on the y-axis? What's the left-handed limit just by this picture? 1, 2, 3, 4, 5, 6. What is this? 7. So the left-handed limit is what? 7. You guys okay with that? You guys see how we graphically can look at the picture? Now, this is as x approaches 4 from the left. What about x approaching 4 now, same value, but from the right side? You go, all these values of x going to 4 from the right? Yes. So they have ordered pairs. Where is the y value on this picture? I know it's missing, but if it were there, what would it be? -2. Good. Isn't that x being -2? It's the y coordinate. So what's this limit here? The right-handed limit. X going to 4 from the right of that function will be what? -2. So this is how we handle piecewise functions. I want you guys to also notice this. Let's put the number 7 here so you guys can see that there. Let me get rid of this. You're just reading that. What's the difference between, let's see if you guys know, the solid circle and then the other circle? What is the other circle? Open. You know what that means? It means I can ask you, what is f of 4? It means that it's defined. If it's an open circle, it's not defined at that location. It's like a hole there. That's a hole. But where is it solid? 7. So this coordinate, though, this will be x is 4, y is 7. The answer is just simply what? 7. So you're communicating to the reader, hey, reader, that solid circle means that's the location of where the point is. It's 4, 7. So the value of the function at 4 is 7. It's not -2. You say, why can't it be -2? Because they're communicating that there's a hole there. At holes, it's not the value. At solid values, it's the value. And all of these values here are solid. Like this point. They're all solid. You guys see what I'm saying? That's what a point is. They're all solid. So if they put a solid point there, they're saying that's what the value of the function is. If it's a dot, it's not there. I mean, an open circle. Okay, so you have some extremely important information. You know what you also know, though, by the way, at 4? What's the limit as x goes to 4 in general of this function? Why do you know it does not exist? Because they're not the same values. You guys see that there? 7 and -2 are not the same. What about f is continuous or discontinuous? Discontinuous where? At that location, x equals what? 4. And why? It's very simple. Right in here, this is the why. You guys know why? Because it doesn't satisfy the definition of being continuous. You see, the definition would be this, if I can get the right thing. The limit as x goes to 4 of the function needs to be equal to f of 4. So because the limit at 4 does not exist and the value of the function at 4 is 7, those are two different things. That's why you say it's discontinuous. However, it is continuous everywhere else. Okay, it's continuous everywhere else. Let me get rid of this. Let me kind of kick it up on you guys. If they say, is f continuous at 0? How do you know that the function is continuous at 0? How do you actually prove it? They might say show. You go, show, I didn't even have a function. All right. Where's 0? X is 0. Sorry. Where is x is 0? Let's find a color. Let's say it's right there. Okay? So what do we know? The limit as x goes to 0. I know we can't even see that. Let's write it down. This is the proof. The limit as x goes to 0 of f of x will equal, anybody know what that is? 1, 2, 3, 4, 5, 6 equals f of 6. I'm sorry, f of 0, which is what? Which is 6. I'm out of space. I'll do it like that. Squeeze it in. And you can see that in the graph. Okay, you see this location 0, 6? Let me put that point there. So, ladies and gentlemen, I'm going to say this, boldly start to proclaim this here, because I think we're out of time. Is that right? We're out of time? No? What time does our class end?
5 minutes.
5 more minutes. Good. But I'm going to boldly proclaim, we're going to start looking at these piecewise functions. And we're going to apply the same ideas. What's the left-hand limit, right-hand limit? What's the value of the function? Functions are not continuous at those locations. This is called having a jump discontinuity. So you go, what are you talking about? Yeah, a jump. Why do you think they call it a jump discontinuity? Yeah, because you're sketching the curve here. You go, what am I doing? I'm sketching this. Then I had to jump to continue. So at those locations, you have what's called a jump discontinuity. So far, you know, functions are not continuous at vertical asymptotes and at jump discontinuities. It's a picture of this. Question? Yes?
I'm thinking about how would this type of graph be related to real life situation, a real life problem?
You'll see. This is just the, you know, what I usually did when I designed this worksheet, I put the arbitrary idea, like here's a continuous function. Oh, here's vertical asymptote functions. And then now here's the start of what? Piecewise. In fact, you have a very famous piecewise function. I mean, first of all, here's a piecewise function. But you have a very famous piecewise function. I mean, I won't maybe tell you it right now. Let's take a look at this. What's important for you to know is you're given now a function and what's called pieces. You go, what does it mean? Well, you got x squared is one piece, and what's the other piece? X minus 4. You guys okay with that? All right. So you're given two functions, but when do you use, I sometimes just say you have a top piece and a bottom piece. So for me, when I see that, I go, here's the top and here's the what? When do you use the top? When, yeah, now I have to start changing my colors. I'm going to get messed up. For x being smaller than 1, you use the what? The top piece. And when x is bigger, I guess I'm going to use, for x is smaller than 1, you use the top piece. You guys okay with that? Oh, typo. Jesus. Greater than or equal to 1. Typo. This is the bottom piece when x is greater than or equal to 1. So I have to fix a couple of those typos. Now, I want you to understand one important detail. You see this number 1? They're gonna be the same number. So if I said to you, you use the top piece for what values of x? Smaller than 1, these are numbers that are what? Well, no, they're to the left of 1. Would you guys agree with that? And numbers that are greater than or equal to 1, these are numbers that are what? They're to the right of what? The number 1. So as you can see, here's where the number 1 is for x, okay? In orange, this is the curve, x squared. Because all those numbers are to the left of what? 1 for x. All the numbers to the right of 1 for x, you use what? You use the line, essentially. This line. And what happens when it equals 1? This is supposed to be greater than or equal to 1. You use the bottom curve. Okay, B for bottom. You guys okay with that? Now, that's why I put this point here for x is 1. This is why on this sheet here, what did I do? I put it like a dot, a solid point. Because you use the bottom when x equals 1. Now, let's see if you're awake. Easy peasy lemon squeezy. What's the limit as x goes to 1 of this function? What are you going to say? I got to get that sound effects. What's this answer going to be? Limit as x goes to 1. How about this? Answer this. What's the limit as x goes to 1 from the left? What's the limit as x goes to 1 from the right? I mean, just looking at the picture, I know this is what? does not exist. How do I know that? Well, you have a jump discontinuity at 1. But they're not going to leave it at that. They're going to want you to find the left-handed limit and the right-handed limit. So, how do we find the left-handed limit in orange? You guys know what you do? It's very easy. Plug in 1. What's 1 squared? Isn't that 1 in the curve? Left-handed limit's 1. And then you say, what about the right-handed limit? How do I get the... What do? You plug in 1 here. What's 1 minus 4? -3. See, isn't it sure enough? Isn't that -3 over here? Isn't that -3 as you approach 1 from the right? Isn't that -3? Did I see my point? Are those two things equal? So that's why it's what? Does not exist. Let's see the last question. What's f of 1 to see if you're really awake? Do you know the meaning of what? Of that solid thing? That means it's negative what? 3. So this is going to come down to this situation, ladies and gentlemen. Can you read the pieces? You use the top when x is less than 1. You use the bottom when x is greater than or equal to 1. Then you say, Mr. Judge, why did you plug in 1 for the top when x can't be that? And I'll say, yeah, you're right. There's really a what here? There's a hole, but I can get away with plugging 1 in there. Why? Because it's approaching from what? From the left. That location is going to be, that's 1, 1, by the way. I know there's a hole there, but that's the location of the hole. You're approaching the y value, which is 1. That's why it's in a limit value, because it's approaching. See, this is why I could get away with saying, what happens when you approach 1 from the left? Well, it goes to, this is really saying y is approaching 1. This is saying y is approaching -3. Okay, because limits are approaching values. They're not actually at the value. So this is your first experience with a what? Piecewise function. Is the function continuous at 1? No. And you might say, why? A couple of reasons. F is discontinuous. Where? At x equals 1. You can say it has a jump discontinuity. They want you to know that. Or you can say it just simply doesn't satisfy the definition. And what you're really supposed to show is all of this information you guys see here. 1, -3, f of -3. This is the work behind the conclusions here for that picture. So, that's what it's going to come down to. Can you read the pieces? Do you know what's to the left? Do you know what's to the right? Can you read that curve? And really, this is arithmetic. 1 squared? 1. 1 minus 4? -3. It's not that simple because like you guys can see, you have to be aware of the concepts, right? But I think it's doable. So we're going to do some more, what do we call this? Piecewise functions tomorrow, and you're going to see some other interesting limit questions. But you've come a long way. I think you could do some of the book work now. Do you guys agree with what I'm saying? Look at the book work. I might be able to go back and look at it too. I don't have my book with me. Maybe I'll run upstairs and get it. And I might just, I don't know. I could just leave your homework as is and say, hey, do what you can for now, and we'll continue. Or I might do something else. Who knows? Okay, take care, you guys. Stay safe. Have a wonderful day. But before we do, we were working on limit questions. You guys really need to know how to have some good feel for what this is before you move on to that. But we were looking at the piecewise functions. Was that true? So I did put some notes here. This is what I'm saying. The limit, which you're going to be concerned with for the most part, is really what's happening right in here. So the left-handed limit is not the same as the right-handed limit, which is why you say the limit does not exist. But the value of the function at 4, because over here in this picture, this is where 4 would be, but the value of the function at 4 is 7. And, the address there is 4, 7. So this is why, I actually added and updated that piece of information in case people needed to see that. Maybe they don't have the skill sets yet by reading that left to right stuff, right? But you'll get there. And then we did an example, and notice that what I'm saying here, I fixed the what? That x is greater than or equal to 1 business. That's the stuff. We don't want that, a perpetual error. So we went through that example, whatever. Now let's look at this example. This is an interesting example. Does anybody know why this example is very interesting? Yeah, in other words, back over here around x is 1, if we compare and contrast. This is around where x is 1. Go back to the last example that we did yesterday, really. At 1, you did have a discontinuity. The left-handed limit is not the same as the right-handed limit. Check your notes. So the limit does not exist at 1, right? This was called a jump discontinuity, because we're kind of doing multiple things at the same time. There's no jump discontinuity here. I'm going to write that in our notes. No jump what? Discontinuity. Here, there was a jump discontinuity at 1. You might say, Mr. Judge, why do they call it a jump discontinuity? Because it's like saying your function for the left piece here was sketch, and then you had to jump to the bottom to finish it off at 1. That's why. Here, there is none of that, even though it's piecewise. So you can say piecewise functions can be what? Continuous everywhere, because you sketch that curve without picking up the pencil. However, let me go into some more details here with that, okay? Let me give you some details. They want you to express, if you ever look at the questions, why. Sometimes they say, show why. Why do you know? So if we look at the limit around 1, and I said to you, what's the limit as x goes to 1 of this particular function? Let's see if you guys can read this. Okay. What's the limit as x goes to 1? Well, remember, you got to go to 1 from what? From the left. You got to go to 1 from the what? To the right. You guys okay with that? So as you go to 1, and you're talking on the x-axis, but it corresponds to the points on the curve, because the limit value is always the what? The y-axis value. Is that right? That point location, by the way, is 1, 1. Is that true? This is the y value. It's the x value. What do you guys know by looking at this picture? What's the limit as x goes to 1 from both the left and the right? It's the same. It's 1. Is that true? So because it's the same, this is 1. And what they really want you to do is write that down, because the limit as x goes to 1 from the left of the function equals the limit as x goes to 1 from the right of the function. They both equal what? 1, ladies and gentlemen. They both equal 1. So that's why the limit as x goes to 1 without the direction is 1. And it's in the picture. And then if you go further, they're going to even want to know, can you tell me what's the value of the function at 1? Bless you. What's the value of this function at 1? Well, it has the dot here. And the dot was in blue. And you go, why did they put the dot in blue? Because how do they define the function? The top function is x squared for what? For x less than or equal to 1. So what that means is f of 1 will be really what? 1 squared. And I know that looks ugly, but let's scroll out. F of 1 is 1 squared because they told you use the top function for 1. And then what is 1 squared? Okay, you guys okay with that? So because the value of the function is 1 and the limit is 1, they didn't say this to you. I'm just putting some notes about this. They didn't ask you, hey, is this function continuous at 1? They didn't. But we're looking at this curve and doing, all those kind of things. So I just want to remark that in this example, yes, the limit is 1, the value of the function is 1, and that means f is continuous at 1. In fact, it's continuous everywhere. So I'm just going with the approach that I have that's a little bit different than your book because I think it's more efficient that way. It's a lot more efficient. And you say, why? Why is it a lot more efficient? Because, when you first start talking about limits, yes, you go through all those little things we talked about. But they can ask you to focus not on that one area. They can even ask you to focus where? Right here. Right? And you say, what do you mean they can ask me that? Well, if I ask you guys, what do we know about this? What's the limit now about 0? What's the limit as x goes to 0 of that function? Do you guys know? What's going on around 0? What do you guys know? I want to say a few things here. Isn't 0 less than or equal to 1? Okay. So what function do you use there? Top one. Is that true? Can I ask you guys a question? I want to give you guys more information here. What kind of function is that on top? That's x squared. Do you guys know something about those functions? It is a parabola, but it's part of the family of polynomials. What's so nice about polynomials? Continuous. So you might even say to me, hey, Mr. Judge, can I just say the limit as x goes to 0 is 0 squared? And I'll say what? Yes. And isn't that 0? Isn't f a 0 because you plugged it in, 0 squared, which is what? 0. So that's my point to you guys. That in the picture, off of that, it's not even a jump discontinuity. This function's continuous everywhere. You could do a functional evaluation. That's kind of the idea. And so I think that's a little bit nicer for people to understand because that's actually what's happening. You get to plug in what? 0 for x, and, your life is good. And 0 squared is 0, and that's the limit. That's the value of the function. You can do that because it's continuous at that location. And, the book gives it to you at the end by surprise. Hey, guess what? This is continuous. I do it in the beginning. That's the difference. Now, if you look at this example, of course, they're going to always want to test you, always, at this, for this value of x. In this case, it's x is -2, right? So you say to me, why do they want to test me on that? Well, because that's where you have, what do we call it? Jump discontinuity. And you go, oh, jump discontinuity. Yeah, that happens at x is -2. So it's not continuous at -2. But why is it not continuous at -2? That's the most important thing, right? Because the limit as x goes to -2 of this function, let's do it a couple of ways now, this jump discontinuity, okay? What do you guys think? The left-handed limit here's where negative 2 is. We're going to it from the left, right? What's going on with these points here? Where are you approaching? Remember, the coordinate here is actually negative 2 comma what? Not negative 1. I think it's negative 6. Is that right? You say, why is that? Where is this location? I know I know, ladies and gentlemen, let's change that color. I know there's a dot there. But you're approaching this y value. Is that right? From the left. What's the value? Yeah, you're approaching this number over here. What is it? It's way over here. This is what it is. It's negative what? So the left-handed limit is what? Negative 6. What's the right-handed limit? This is from the left. Limit, x goes to negative 2 from the right. Now approach it from the what? From the other side. You go, what's the other side? Well, yes, you're approaching the x values from the right of negative 2, but these are corresponding to points on the curve. What's this address now? Well, that address is what? Negative 2 for x, and then positive what? 3. Isn't that 3 right here? Okay. Is that 3? 1, 2, 3, 4, 5. I guess it is. So what is the right-handed limit going to be now? 3. All right. So that's going to be 3 here. I'm going to put it in green because that's 3. Actually, it's not 3. It's actually going to be what here? Is that really 3? Yeah. Well, I'm going to change this on you guys. It's not 3. It's about 3.1. Okay, now let me share with you what I did to you guys. Okay, let's share with you guys what I did. Because let's say, ladies and gentlemen, you don't even have a picture. Bless you. Let's say you don't even have a picture and they give you this function here. Okay, you go, oh, Mr. Judge, how do I handle this without a picture? Oh, my God, I don't know, right? And so it's going to go back to, okay, let's read it. Let's read this. On top, when do you use the top function? Okay, for x is less than negative 2. Do you guys know that means in terms of negative 2, the numbers that are less than negative 2 are numbers that are what? To the left of negative 2. We use the bottom function. When do you use that bottom function? Yep. You say, why do I know? I use that for numbers that are to the right of negative 2. Of this negative 2. How do we know it's to the right? Because those are the values of x that are bigger than what? And those numbers are to the right of negative 2. You guys okay with that? All right. So I think we're coloring what? I don't remember the colors. I think the left was orange, right? And the right was green. Okay. So you might say, what do I do now? Well, here's what you guys can do, okay? Yes, obviously, as x approaches negative 2 from the right of the function, because it's approaching negative 2. It's getting close to negative 2. You're going to use what? Pi. If you said, what's the limit as x goes to negative 2 from the left, because you are approaching, you're going to say 3 times negative 2, which is what? -6. Because you are what? Approaching. So even if you didn't have the graph, and I know some people are like having sleepless nights because they go, Mr. Judge, my graph, can I get out that TI at least? Oh my God, you can still answer this without the what? The graph. Because the limit is approaching. The book calls that direct sub, by the way. Directly substitute. Now, you might say, what if they said to me, what's the value of the function at -2? Well, you're going to say what now? This is not an approach. This is at -2. Which are you going to use when x is -2? I don't know. What does it say? I'm going to get out my highlighter. Use the bottom for x being greater than or equal to -2. So what is the bottom function? It's constant. It is what? Pi. So you can use the information without even looking at the graph. Okay. And it's just about, can you read the piecewise function? That's it. So what does that conclusion mean if I said to you guys, you laid the groundwork, right? And you said, oh, what's the limit? X goes to -2 of this function. What does that equal? What does that equal, ladies and gentlemen? Does not what? Because you knew your definition. So you know your definition? Good. Does not exist. Is this function continuous at -2? No, you can write that down, but notice what I did. I got all of this piece of information just by reading the function. That's it. I didn't even have to do the graph. So if you look at your book has some nice kind of pictures and tries to, but we have to talk about the pictures and everything. But you can also do it without the graph. Now, you may not realize, but you know this function, the absolute value of x? This is the graph. It's that V. Do you know that this curve is defined piecewise? And we're gonna deal, this is gonna be a big deal. So I'm gonna say to you guys, your function f of x is x when x is greater than or equal to 0. This function is minus x when x is less than 0. That's the definition of the absolute value function. Okay, you guys with me on that? So, let's say they just gave you the definition. And they say, what's the limit as x goes to 0 from the left of that function? What do you guys have to know? I'm forgetting my colors. I don't know. What is it? To the left of 0 is orange. So this is a left-handed limit, okay? Which function do you use? Which one is to the left of 0? Top or bottom? How do you know bottom? Because any number that is what? To the left of 0 has to be negative. All right, then what do I use? This. All right, so I get to now do direct sub. You say, is that negative x? No, plug in what? 0. There's no such thing as negative 0. That's negative 1 times 0. And that equals what? 0. So your left-handed limit equals what? Equals 0. All right. What's the right-handed limit? What's the limit as x goes to 0 from the right now? You say, well, if you're going to 0 from the right, you may be able to guess. I got to use what? The top curve. Why? Because all the numbers that are to the right is 0. What's the story? They're greater than 0. So you're going to use that top function. So notice this. You don't even have to look at the curve. I didn't even look at the curve. So you say, oh, I get to use the top. Yes. And so you go, is that just x? I'll say, no. You're plugging in the value of x to be what now? 0. And there's not even any computation to do. This, ladies and gentlemen, is the what? Is the right-handed limit. So they're both 0. What does that actually mean? The limit as x goes to 0 equals 0. Good job. You guys know this stuff by now. Is that right? Did you guys see how all of a sudden some of these definitions start to gel and you say, okay, you go, okay, I see. It's the same value. How about this? What's the value of the function at 0? And you're just looking at the what? The piecewise function. X equals 0. What do you guys use? The top or the bottom? How do you know the top? Because greater than or equal to 0. Oh, okay. So that's going to be just what? 0. All right. When the limit equals the value of the function at the location, what do you guys know? F is what? Continuous at 0. You're testing the 0. And they love to test those locations. That's what they're going to test you on. Yeah, they'll throw a curve and say, hey, is this continuous at 1? Or what's the limit as x goes to 1 of the absolute value function? And you go, oh, a linear equation at 1 now. This is x is 1, okay. You're using the top curve. The top is a nice polynomial. They're continuous everywhere. Functional evaluation. You're not supposed to know that until, the next chapter. Look at the picture. Can you draw this curve really everywhere without picking up your pencil? Especially at the number what? 0. Now, that's a special location. You have a corner there. We'll study corners, but not now. We're not studying corners. We're just talking about limits and continuity. So you can do this graphically and what? Analytically, numerically, if you could just read it. Should we do this one too without looking at the curves? You might say, Mr. Judge, what do you think they're going to ask me limit questions? Easy. Can you answer a limit at -4? If I said to you, what's the limit as x goes to -4 from the left of that piecewise function? Well, if they say x is -4, isn't that values of x that are to the what? Left of -4? Because they're smaller. Is that true? Okay, then what do you have to use? X squared plus 1. So plug in the value of x. What's that going to be? -4 squared plus 1. And what's your arithmetic? 16 plus 1, which is what? 17. So the left-handed limit is what? 17. Limit x goes to -4 from the right of the function. Now, again, What do you guys use now? What value is you got now? Top, middle. You got top, middle, and what? Bottom. What's this going to equal? It's really easy. This is going to equal what? 8. How do you guys know it equals 8? Well, isn't down here x, the values of x that are to the right of -4 are going to be less than, right? -4 less than or equal to x. Those are to the right. That's how you know. And again, they're to the right of that special number we're looking at, -4. So this equals what? It's a constant. It's 8. What do you guys know about this? What are they going to say? In terms of just the limit. They're going to say what? The limit x goes to -4, the function, what do you guys say here? Does not exist. Why? They're not the same. What's the value of the function at -4? Which do you use? The top, the middle, or the bottom? Why the middle? Because it's equal to. So you can answer all of these questions, ladies and gentlemen, by just looking at what? The piecewise function and reading it. So if you know how to read that piecewise function and you know definitions of limits, the idea approaching from the left of the value, approaching from the right of the value, you can actually answer a lot of questions. And moreover, is that function continuous at -4? No. F is what? Discontinuous. At x is -4 because the limit does not equal the value of the function. D and E is not 8. Notice the graph. -4 is down here. Notice again, as you're approaching from the left, right? I guess that was what, 17. As you approach from the right, well, that's constant. I guess that was 8. It'd be very difficult. I mean, I guess you might deduce this is what? 2, 4, 6, 8, 10. You could deduce what it is on the graph. And so these are by 2, 12, 14, 16, 18. So that's in the middle. That's 17. So you can still deduce the answers graphically, but the point is you actually don't need it to do it numerically, really, or I should say arithmetically, if there's even such a term. Arithmetically. Readily, arithmetically. Now, which one, what do you think they're going to ask you also about? What special number do you think they're going to ask? 2? Absolutely. They're going to want to see, do you know what to use for the 2 value? Now, there's where 2 is. Okay, now you guys know just by looking at what? The graph. How about if, can I change notation on you? Are you guys? Can I use calculus 2 notation? You don't say, no, don't use that. X goes to 2 from the left. Y goes to what number? 8. X goes to 2 from the right. Y goes to what? Both directions, they're going to the same what? Or isn't the y coordinate going to what? 8 as well? So that means the limit, calculus 2 notation, x goes to 2, y goes to what? 8. You guys know the coordinates of this? This is 2, 8. Apologize to you guys. I just threw in calculus 2 notation. It's a little bit easier to write down, don't you think? It's a lot easier. Anyway, I'm just throwing that out there because that's where we're headed, calculus 2, right? The value of the function at 2 equals what? 8. How do you know? There's a solid dot there. If you had to use, you said, Mr. Judge, I don't know. I'm a little concerned about graphs. I don't have a TI, and on the test, you're not going to let me use that TI to graph, really, I guess. I don't know. How would I do this without a calculator? Poor me. Well, around 2, which curve is to the left? You guys know what I mean? This is top, middle, and bottom. Which one are you gonna? What is to the left of 2? Which interval is to the left of 2? The middle interval. Okay. So if you had to do that, you said, "What's my limit?" And limit x goes to 2 from the left. What's the function? You're going to use 8, the middle. That's a constant. Anyway, you guys don't know this yet. So I'm going to say that's going to be what? 8, because you're going to use the middle. What about, then that's to the left of 2. Which one's to the right of 2? Bottom. So if I said, okay, now the limit x goes to 2 from the right of that function, you plug in what? 2 cubed, which is 8. So I didn't even have to use any of that. I didn't have to look at the graph. I just have to know what values of x are to the left of 2, what values of x are to the right of 2. I just have to know how to read an inequality. And that's it, how to read that. And you have the corresponding graph. So ladies and gentlemen, you know, I'm just putting it all together graphically and numerically. Now, this is a nice one, because this is a little bit different. And you say, how is that different? Well, what's the deal now? You kind of, what do you have? They're going to ask you questions around what? Looks like, see this x is not 0 and x equals 0? Okay, x is not 0, x equals 0. They're going to ask you limit questions now. See if we can figure this out. The limit as x goes to 0 from the left of 1 over x. Now, let's say, again, forget the curve. You don't even look at the curve. Let's say you're looking at this. You don't even remember the curve. And you go, I don't know what the left-handed limit is for 1 over x. Darn it. All I have is my what? My TI calculator. And let's see. Do you guys know? Can you give me a number to the left of 0 that's close to 0? Don't use -1. It's to the left, so it's going to be negative. But it also has to be close. 1 divided by -0.00000. Is this going to be close to? Is that value of x, because it's 1 over x? Is that x close to 0 from the left? It's negative, but it's also 0.00001. What happens when we plug that in? What do you get? Negative E11. That's scientific notation. You guys know what that is? It's -1 with 11 zeros. Don't put this as an answer. Don't put this as an answer. If you do, it's going to be wrong. What do I put? Negative infinity. If you look at the picture, aren't you going to negative infinity? You guys see what I'm saying? You can think of the picture because back in the old days, we didn't have calculators. Well, I think we did, but in the old days, we had to think of this picture. We had to know curves. Every B-STEM student should know. And so the limit, you guys know again, as x goes to 0 from the what? From the right of 1 over x, what's that going to equal? That's infinity, just by looking at this picture again. If you said, I have a picture block. All right, 1 divided by, give me a number to the right of 0, but it's close. Close to 0. How close? Arbitrarily close. Really, really close. Okay, just put this. Is that close? Because it's 1 over x. Got to use these x values. You go, okay, this is my answer. If you write this down, that's wrong. What are you going to write down? Positive infinity. Is that right? So if they go to two different places, we already know, because we've seen it over and over again, x goes to 0 of 1 over x. That's the function does not exist, right? All right. But then you said, okay, Mr. Judge, we know this. Vertical asymptotes happen when x equals 0. We set the denominator equal to 0. I know I have a vertical asymptote because you've just been doing this, showing me this stuff forever. But what do you think they just did when they gave it to you as a piecewise function? See, they're going to ask you now, what's the value of the function at 0? Can you read this? Yeah, what are they saying? The value of the function equals 4 when x equals what? And they put a dot out here where 4 is. That's location 0, 4. So you're going to say the value of the function equals what? 4. So for this picture, you don't say the function's undefined. You say it's what? 4 at 0. Because they put a point in. You say, could they do that? Yeah, they can define it piecewise any way they like. So what they're saying is use the top piece for values of x that are not 0. Use the bottom piece for value of x that are zeros. So they actually put a point in. It's no longer undefined. Now, does that mean it's continuous? At 0? No. F is still what? F is still discontinuous at x equals 0. Do you guys know why? Because they may tell you, hey, explain why. Why is it discontinuous? Because the limit does not equal the value of the function. So they really like to ask you, hey, don't guess, because a lot of times people just guess. Oh, yeah, continuous. Oh, yeah, discontinuous. No, they'll say, please explain why. This is the explanation. All right, they want to know, do you know how to read this picture? Do you know how to read the function? What do you think they did here around 0? They did the same thing. What did they do? They put a point. So they said, oh, I think when they're just saying, at 0 here, they say f of 0 now equals what? -2. And that should make sense because when you read this, they say the value of the function is -2 for and when x equals 0. Sometimes they say the word if, or they say the word when. Now, could you guys tell me what's the limit? If you said, Mr. Judge, how do I find the limit of this function at 0 from the left? Okay. And that's really 1 over x squared, okay? Well, what should you know? How does that curve behave? It behaves like this. There's a vertical asymptote at 0. It's the volcano. So what's your answer? Infinity. What about to the left of 0? What's my answer? Infinity. Same thing. So you go, oh, does that mean the limit's infinity, regardless of the direction? Irregardless of the direction, the answer is yes. But what if you had to use your calculator because you said, Mr. Judge, I am graph deficient. I don't know what any graph looks like. How can I answer these questions? Okay, give me a value of x to the left of 0 that's close to 0. Can I use that negative 0.000001 again? But I know I have to do what? I have to square it? Yes, you can do that. And now you get a very big number. That's very big. 1 times 10 to the 18. That's 1 with 18 zeros. So that's to the left. What about to the right? 1 divided by what? To the right is 0, but close. It's positive. Is that number close to 0? Yes. Square it. What do you get? Another very big what? Number. So you can actually numerically do this. Does your book tell you on your homework to do these kind of things? Do you guys know what I mean? It does kind of. It says use these values of x. They want to see, can you plug it in a calculator? They want to see, hey, do you understand, what you're looking at? Getting close to a number. They want to know that. So you get to use a calculator and you get the same answers, right? Is your function continuous at 0? No. F is discontinuous at x equals 0. And then you say why? Essentially because the limit, the limit does not equal, it's the same reason. Because the limit of the function does not equal the value of the function. I can't even write it down. So, ladies and gentlemen, this is a lot of good, powerful detail. All right, now, here's what I want to talk about. This is called a removable discontinuity. And you might say, what's a removable discontinuity? What do you guys think? What are you guys looking at? There's a hole in the curve. You go, Mr. Judge, can there be a hole in the curve? Yeah. So let's see if you're awake. If I said graphically, can you read this around that hole? This is where x is 4. Graphically, as you approach x from the left of 4, what's the y value? You guys know what this coordinate value is? This is 4, 3. But there's a hole there. But this isn't the value of the function at 4. This is getting close to 4. So what's the left-handed limit? What's the limit as x goes to 4 from the left? Good. What's the limit as x goes to 4 from the right? How do you know it's also 3? Because as you approach 4 from the right, you're still approaching that same location where y is 3. All right. Now, what do you guys think that means? That's pretty good. That means what? What's the limit as x goes to 4 of that function? What does that equal? 3. Because the left-handed limit equals the right-handed limit. And that's what I'm saying right in here in that summary. So that's what I added for you guys. Some of these things I added new, just in case you say, I'm going to look at those notes, right? And then what's the value of the function at 4? Why is it undefined? You go, Mr. Judge, You're telling me the value of the function at 4 is undefined. Why is that? There's a hole there. It's not defined. Isn't that simple? Got to learn the details. Learn these details. So hopefully by now you're starting to say, okay, I can see your point. You go, yeah, at first I was a little sketchy, and now I'm going, okay. And of course, next chapter talks about continuity. It's the same questions. So you're killing 2 birds with 1 stone. What about this picture? Do you guys realize? Let's stop and think. You may not realize this. They may ask you, without even looking at that picture, right? They're going to say to you guys, what's the limit as x goes to 3? Now, they're going to give you another rational function here. Okay, this is a good question to start with. Here's a rational function. And if you said, you know, I'm going to start off by plugging that in, right? I'm going to say, okay, 0 squared minus, I'm going to plug that in. 3 squared minus 9 over 3 minus 3. Okay, this is a very good example of a point I want to make. So if you just plugged in the value and you're going, I think this is nice and continuous, right? Do the arithmetic. 9 minus 9 over 3 minus 3. Do you guys know what that equals? Yeah, that's 0 over 0. I hate to break the news to you. This is another scenario that calculus students need to be very, very familiar with. This is a calculus concept. What is 0 over 0? That's called an indeterminate form. Nd what? Determinate. What does indeterminate mean? You know what it means? Can't determine. You know what I hate to do with texting? Some people ask me questions. You know what I do? IDK. What does IDK mean? I don't know. That's indeterminate. We don't know. But just because we don't know doesn't mean there's what? There is not an answer. There is an answer.
There's a hope that you have to, but the limit still exists.
Well, here's the thing. Whenever you're in an indeterminate form, I'm going to use kind of the dirtiest word in math. It's not even the dirtiest word. It became the dirtiest word. There's a lot more dirty words in math. This is, you know what the fix, if you're in an indeterminate situation, there's an easy fix. The fix is easy. Go back to the function. You say, what's the fix? Use what? Algebra. That's the new dirty word in math. Algebra. The dirtiest word in math used to be proof. You say, okay, you got to prove this is proof. Then that was a dirty word. You go, oh, proof? Yes. Proof is dirty. Then algebra became the dirty word. Well, this is how you always fix the indeterminate situation. You got to go out to algebra and you go, what do you mean by algebra? Well, what are you guys looking at? Because remember, you might tell me, isn't that a rational function? And I'll say yes. Oh, okay. Does that mean I set the denominator equal to 0 and I say, oh, x minus 3 equals 0, which means x equals 3. You say, oh, I know I have a vertical asymptote. We've been working with these functions and limits. We've seen a lot of those. And I'm going to say, yeah, but there's one little thing. There is no vertical asymptote there. And you go, what? You've been lying to me all this time? And I'll say, no, but every rational function they gave you was a simplified rational function. So if that rational function was simplified, then yes, you would have a vertical asymptote at x is 3. I'm going to say that again. If that rational function was simplified, then you would have a vertical asymptote. If that rational function was simplified, you'd have a vertical asymptote. The problem is, or not the problem, the good news is, you can simplify this function. And that's the dirty word. You say, how? Well, there was a process known as simplifying rationals in algebra. And how you simplify rationals is you had to know how to factor. And so the denominator is not factorable, but the numerator is. How do you factor the numerator? X plus 3x minus. That's a special factor from beginning algebra. The course they banned it from students because they said everybody can do it. There's a long story to that. I'm not even going to get into the long story. I'm not going to go there. So what do you guys do? You cancel the x minus 3, and what do you get? X plus 3. So you go, what? You mean that rational can be simplified by factoring and canceling? Yeah, now this is y equals, and this is y. So in other words, that curve, ladies and gentlemen, is really equal to x minus 3, but x can't be 3. You got to throw 3 out. The value of x is 3. So if the value of x is 3 is thrown out, go back to this picture. This is the reason why there's a hole in this line. You see, this line, this is a line. This is the equation. Y is x minus 3, where you have the what? From beginning algebra, you got the y-intercept. The slope is 1. But when x is 3, it's gone. It's called a removable point or a removable discontinuity. That's why you just see a line. You go, I'm expecting something else. No, it's a line with a hole in it. So they're going to ask you that question right in here. And you go, okay, what if I invested in the fix in the algebra? And then you say, Mr. Judge, how do I answer the question now if I know that what? That's the same as this question. The limit x goes to 3 of x minus 3. This question is exactly the what? The same. I'm sorry. This would be an x plus 3. Do you guys know what the answer is? It's very simple.
6.
It's going to be 6. How do you know? Direct sub. By direct sub, you say 3, you get to directly sub in that value of x, and you get what? 6. Why is that by direct sub? Because this is a linear equation. More importantly, it's a polynomial. Remember, this is an approach. So I get to add that 3 for x right in here. And 3 plus 3 is 6. So if you go back to this picture, you go, oh, is that why here? Holy moly, isn't that? Oh, wow, exactly, ladies. And that's what I spend my nights editing at night when my wife's looking at me giving me that stink eye and says, hey, you ever going to pay attention to me? What about me? The baby's jumping on my head and I'm on my computer. This is what I'm doing, ladies and gentlemen. Look at that. Oh, my God. You guys are looking at a very, very big deal. But the dirty word is what? Algebra. And it's going to be factoring. Now, it's not, and then, of course, they're going to always ask at that location. This is the idea. And all the other examples work the same way. Like this example, of course, they'll ask you for the limit. as x goes to -2. Oh, x squared minus 4. And sure enough, you plug that in for x, you're going to get 0 over what? 0. And what is this? This is indeterminate. Indeterminate means can't determine. It doesn't mean that there isn't an answer that you can't determine. It means, in short, use what? Algebra. That's actually what it means for us, in all honesty. It means simplify your rational. That's all. That's all it means. Your book doesn't even tell you that stuff, right? It means simplify that rational by some algebra. So it says, you're going to say x plus 2, x minus 2 over what? Good. And so what does this equal? Limit x minus 2, and x is going to where? -2. What do you guys get to do? Plug it in. What's -2 minus what? 2. So I got to go here. See that goes in here. And what does this equal? It's -4. You see, there's no coincidence that if you look at this location here, this is when x is -2, and that's when x is -4. That hole happens at -2, -4 here. Okay, however, what's the value of the function at -2? There's a hole at -2. What do you guys know? Ooh, got you. A limit is an approach. The value of the function at -2. What's this? Undefined. Good. Why is it undefined? There's a hole there. It's somebody put a hole. They removed a point. They removed that location. That's why there's a hole. They can put it back.
That's why it's called removable, right?
You said, Mr. Judge, are you reading my notes? Did you jump ahead? See this? You can have a removable discontinuity, and they can add a point at some other location, or they can even add it at that location. They can put it back, but it has to be defined piecewise. So if you read my notes further, you go, is that what you spend your nights doing as the Dodgers are losing? That's what I'm spending my nights. My wife says, you're going to eat your taquitos. They're getting soggy. I'm like, almost there. Dodgers are losing, and I'm almost there. I got to put some points back for this removable discontinuity. Dodgers are losing, but my students aren't. That's the way it is, ladies and gentlemen. People don't believe me, but well, you say, why would I do this? Because the truth is, I'm going to tell you guys like I tell my own daughter. How can I put it? My life didn't change until I started doing my homework every day. Every day. You know, Jaime Escalante taught me calculus, but I teach you guys a lot more than he ever did. You know, but he was my calculus teacher, so I learned from him. So I do a lot of things that he's done, but I also do a lot of things that he never did. So, yes, he gave you handouts and stuff, and he certainly didn't go in lockstep with the book, section 1, section 2, blah blah blah, because teaching is an art. It's not a science. So that's how he approached it. But nevertheless, ladies and gentlemen, yeah, this is the deal. So it's important for me to be able to do this stuff because I think it's very important. I mean, I don't know. So I don't know. Maybe I just remember what it's like being a student. I never forgot. And so, my daughter, she sees there, she sees me. What does she say? She finished a math degree. She majored in mathematics. I never told her to. And then she sees me. She goes, you know what, Dad? I wish I had you for all my classes. I said, huh? What? Oh, okay. Yeah. I guess that's a compliment, but okay. So yeah, Ashley, me too. I never had her in my classes. You can't really do that. That's kind of unethical. You guys know what I mean? Some instructors do. Huh? Very much so. You know, she can see me writing the test I'm going to give her. She could be looking over my shoulder. I said, Dad, you're going to give me that limit question as x goes to 1, where there's that removable discontinuity? Oh, that's the kind of question my dad's going to ask. You can't do that. Some instructors do. I've seen them do it. And I've looked at them. I remember, oh, don't tell anybody. This is good. This is good. Oh, this is really good. I once had an instructor. She asked me, can I switch courses with you next semester? Because she wanted the course that her son was going to take. And I already knew that. And you know what I said? I said, no. I didn't tell her why. I didn't say, I know what you're doing. I just said what? No. That's it. Sometimes saying less is saying more. But I won't do that. Now, if my daughter asks me questions, will I help her? Of course. I'm not helping her on a take-home test, but if she got stuck and she had questions on homework, and sometimes she did in calculus, I'd say, oh, Ashley, you know what you do? You just simplify that fraction and then evaluate the limit. That's it. There's a hole there. So what would happen here for you guys, right? You're going to get what again? 0 over 0. What's the deal? That's indeterminate. What do you guys use? Use algebra. Factor. X plus 1, x minus 1 over. Get rid of that. You just get a nice x plus 1. That's the curve y equals x plus 1 with a hole where an x equals 1. So if you take that limit now, what does that give you? Plug in the 1. What's 1 plus 1? 2. Direct sub. And just to kind of, that's where 1 what is? 1, 2. But there's a hole there. And f of 1 is what again? If there's a hole, undefined, ladies and gentlemen. So there's a way for you to do these things without using, without even the graph, okay? And that kind of is going to show up. That's going to happen. So, I'm going to leave this last example for you guys to do. Believe it or not, you say there could be a hole for a parabola? Yeah. If you're going to look here at the limit, as x goes to, I believe, negative 2. Uh-oh. There's a problem here. This is not the right curve. Is there a problem? Yeah, I'll fix it. Something's not right. You know why it's not? Oh, no. There's no problem. Shh. I don't have to fix anything. How do I know there's no problem? At x is negative 2 over here, you should have a what? There's a hole there. So I'll have you guys look at that limit question for this thing here. Of course, we'll continue tomorrow. We'll put some more of these ideas together, but hopefully you guys can be doing more of your homework now. You guys know what I'm saying? Hopefully a little more of your homework starting to make some sense. We can finish this tomorrow. But anyway, take care. I forgot to take roll. Darn it. Let's do that really quick. See who's here, who's not. Jessica Morales. Okay. Genevieve Barrios. Julian Cabrera. Victoria Castillo. Elizabeth de la Cruz is not here. Destiny. Okay. Shannon here. All right. Alejandra Flores. All righty. Edgar Gonzalez. All right. Laura Gonzalez. Laura. Samantha Gutierrez. David Guzman. All right. Cora Pot here. Jiayu Lee here. Jimmy Lee here. Adrian Lim. Okay. Sandra Yamas. Hoon Lee. Christian Martinez. Brian Malgar. Okay. Sorry, I can't see. Alexandra Mendez Contreras. Valeria. Christian Morial. Okay. Damian Munoz. Aye Mio. Gabriela Ramirez. Jaime Ramos. Giselle Rivas. Sebastian Rodriguez. Alacorn Saldivar. Eric Sun. Thurian Thiep. All right. Jocelyn Cezili. Alberto Vasquez. Okay. Olivia Velasquez. C.U. Wang. Lauren Wu. Jun Kong Si. Haley Yan. Sarah Zahui. Patrick Zamora. Okay, and I think there's probably people online. Nobody's saying anything. Okay. All right, you guys. I'll see you guys tomorrow. Take care. Stay safe. We'll continue